All right, let's dive into a topic that might sound a little textbooky, but I promise you it's actually running the show all around us. We're talking about chemical equilibrium, and it's not some static, boring state. It's nature's ultimate balancing act.
Okay, I know. It sounds like the beginning of a really weird joke, right? But seriously, the answer to this question, it's the key. It's the one thing that's going to make this whole idea of chemical equilibrium just click into place. So picture this. You're out on the water in a little rowboat. It's peaceful. And then you notice a leak. Water is starting to seep in. What do? Well, you grab a bucket and you start bailing. This simple little scene, it's the perfect model for how countless chemical reactions actually work.
So you've got two things happening at once, right? Two opposing forces. There's the leak, bringing water in, and then there's you, bailing water out. At first, you're probably bailing like crazy, but after a bit, you find a rhythm, a pace, where the amount of water you're throwing out perfectly matches the amount of water that's leaking in. And what happens to the water level in the boat? It stops rising. It's stable. Now, this is the absolute key takeaway. Just because the water level is constant, it does not mean the action has stopped. No way. The boat is still leaking, you are still bailing, water is constantly moving. This isn't some frozen, static situation. It is a dynamic balance. That word, dynamic, is everything here. So how in the world does a leaking boat connect to chemistry? Well, think about it. Just like the leaking and the bailing, a ton of chemical reactions are actually a two-way street. There's a forward reaction, where your starting chemicals, the reactants, make new stuff. But there's also a reverse reaction, where that new stuff breaks back down into what it started as. And here it is, the official definition. Chemical equilibrium is simply that point where the speed of the forward reaction, our bailing, is exactly the same as the speed of the reverse reaction, our leaking. When that happens, the total amounts of all the chemicals involved just stay constant, just like the water level in our boat. See? It makes sense now. And to show this two-way street, chemists have a special symbol, this double arrow. It's a signal that says, hey, this reaction is going both ways at the same time. So, in this example, hydrogen and iodine are making hydrogen iodide, but at the exact same time, hydrogen iodide is breaking apart to reform hydrogen and iodine. It's this constant, perfectly balanced dance.
Okay, so if reactions have this balance point, you might be wondering, well, where is it? Does the reaction prefer to make a lot of products, or does it kind of hang back with the reactants? Turns out, chemists actually have a way of keeping score. It's called the equilibrium constant, or KEQ for short. And don't let the name scare you. It's really just a simple number. It's a ratio that compares the amount of products to the amount of reactants once that dynamic balance has been reached. And that one little number tells you the entire story.
It's pretty straightforward. If KQ is a number bigger than 1, it means when you're at equilibrium, you've got more products than you have reactants. The ratio is top-heavy. This tells you that the reaction really likes to go forward. The balance point is way over on the right side of that double arrow. And you probably guessed it, if the KEQ is less than 1, the exact opposite is true. The ratio is bottom-heavy. You have more of your starting materials, your reactants, left over at equilibrium. The reaction just doesn't proceed very far before it finds its balance point over on the left side of the equation. Okay, we've got our system in a nice, happy balance. This is where things get really, really cool. What if we don't like where the balance is? What if we want to force the reaction to make more product? Well, we can. We can actually poke the system, or as chemists call it, apply a stress, and make it shift. And the rule book for how to do this is called Le Chatelier's principle. All it really says is that if you have a system in equilibrium and you mess with it, you disturb it, the system will fight back. It will automatically shift its balance to try and undo what you just did. Let's jump back in our boat for a second. Let's say the leak suddenly gets bigger. That's a stress on our system, right? Now water is coming in faster than you're bailing it out. So what do you do to counteract that stress? You have to bail faster. You shift your effort to get more water out, and you keep going until you find a new, slightly higher, but stable water level. You find a new balance. It works the same way in chemistry. There are a few common ways to stress a reaction. If you dump in more of a reactant, the system says, whoa, too much of that, and shifts to use it up by making more product. If you take a product away, the system says, hey, where'd that go? And shifts to make more to replace it. It's incredibly predictable. The system always pushes back to find a new equilibrium. So, why should you care about any of this outside of a chemistry class? Well, let's look at a really beautiful real-world example of this principle in action that might just be in your own backyard. You've seen hydrangea flowers, right? They're amazing, vibrant colors. Well, that color isn't just about genetics. Nope, it is a living, breathing demonstration of chemical equilibrium. Whether that flower is blue or pink is decided by the availability of aluminum ions in the soil, a system that is in a constant shifting balance. So here's how it goes down. If the soil is acidic, that acts as a stress on the system. This stress shifts the aluminum solubility equilibrium, making more of it available for the plant's roots to suck up. As the plant absorbs more aluminum, those ions get into the petals and interact with the pigments, and the result? You get these absolutely brilliant blue flowers. You've literally stressed the chemical system to get a different result. And what if the soil is basic or alkaline? Well, the equilibrium shifts in the exact opposite direction. Way less aluminum is available to the plant, so it doesn't get into the pigments and the flowers just stay their natural red or pink color. So any gardener who adds stuff to their soil to change the color is actually being a hands-on chemist, manipulating a chemical equilibrium. So there you have it. From a simple leaking boat all the way to the color of a flower, chemical equilibrium is this constant dynamic balancing act going on all around us. It's not some end point, it's a continuous process. So my question for you is this. Now that you know what you're looking for, where else are you going to see it? Think about the fizz in a soda can, or even the delicate chemical balances happening inside your own body this very second. It is absolutely everywhere.